In the dark, frigid void beyond Neptune lies a vast and mysterious region where the ancient remnants of our solar system's birth drift silently through the darkness, perfectly preserved by the deep freeze of space. To reach this shadowy expanse from Earth, we must travel past the rocky planets, flying by Mars and then beyond the swirling storms of Jupiter and Saturn. Farther still, out beyond the blue giants, Uranus and Neptune, we finally reach our destination. Welcome to the Kuiper Belt, a vast ring of icy debris encircling our solar system like a frozen halo. This isn't just a collection of distant rocks, it's a time capsule from 4.6 billion years ago, holding the untouched building blocks of our cosmic neighborhood. It is home to several dwarf planets and mysterious objects that have left many astronomers scratching their heads. Shadows of our solar system, and piece together clues about its history, about planetary formation, comet activity, and even the origins of life. Before we knew for sure that the Kuiper Belt was real, astronomers suspected that something existed beyond Neptune. For decades, everyone's favorite dwarf planet, Pluto, was thought to be an isolated object in the outer solar system, but something didn't add up. Its small size and unusual orbit suggested that Pluto wasn't alone, and that maybe it was merely one of a number of yet-to-be-discovered distant objects. In 1951, astronomer Gerhard Kuiper predicted the existence of a belt of icy objects just beyond the orbit of Neptune, but without telescopes powerful enough to detect these objects, the idea remained theoretical for decades. That changed in 1992, when astronomers David Jewitt and Jane Liu discovered the first confirmed Kuiper Belt object, known as 1992 QB1. Pluto and its moon Charon were both discovered before 1992 QB1, Pluto in 1930 and Charon in 1978, but these objects were only confirmed as KBOs after the 1992 KBO. Since then, thousands more Kuiper Belt objects have been identified, populating this distant region beyond Neptune. To grasp the true scale and position of the Kuiper Belt, let's imagine we're traveling in a spaceship, starting from the Sun and moving out towards the outer edge of our solar system. As we move along our journey, let's compare the Kuiper Belt to both the more well-known asteroid belt and the less well-known Oort Cloud. Starting near the Sun, we zip past the rocky planets, Mercury, Venus, Earth, and Mars. Between Mars and Jupiter, we see the asteroid belt, made up of the leftover materials from when our planets formed. A thin, spread out ring of rocky debris, the asteroid belt is about 2.2 to 3.2 astronomical units away from the Sun and about 1 astronomical unit wide. As a reminder, 1 astronomical unit is equivalent to the distance from the Sun to the Earth. Most of the known asteroids reside in this part of our solar system, ranging in size from the largest asteroid, Vesta, at 525 kilometers wide, almost the distance from London to Belfast, to the smallest objects, some of which are just tens of kilometers across. However, despite residing in such a large space, the total mass of all of the asteroids in the whole asteroid belt combined is only about 3% of the mass of the Moon. Beyond the asteroid belt, we encounter the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, colossal worlds that dominate the outer solar system. Finally, as we pass Neptune's orbit at 30 astronomical units, we reach our destination, an even more remote, icy frontier, the Kuiper Belt. This vast expanse stretches from 30 to 50 astronomical units, and is home to a range of intriguing objects, from frozen relics of the early solar system to dwarf planets including Pluto, Haumea, Eris, Makemake, and countless other smaller objects. Like the asteroid belt, the Kuiper Belt contains ancient debris from our early solar system. In fact, Kuiper Belt objects are considered some of the oldest surviving pieces of our solar nebula that originally formed the planets of our solar system. And so, at one point in the very distant past, these stray pieces might have been able to come together to form yet another planetary body. However, Neptune's gravity prevented the icy objects from coalescing and never allowed them to form something new. Unlike the asteroid belt, which is primarily made of rocky material, the Kuiper Belt consists of mostly frozen methane, ammonia, and water ice, forming a frozen, thick, donut-shaped ring of debris. The Kuiper Belt contains hundreds of thousands of large icy bodies bigger than 100 kilometers across, and more than 1 trillion comets, not to mention smaller debris and dust. And the average distance between objects is so large it can be hard to imagine. Each of those objects is, on average, between 0.02 to 0.1 astronomical unit apart. Imagine 10 million kilometers between objects. Here, in the dim outer reaches of our solar system, these icy bodies drift in near silence, preserving vital clues about the origins of planets and comets. But it doesn't end there. That was just the main region of the Kuiper Belt. Overlapping the outer edge of the main region is another area of Kuiper Belt called the scattered disk, which continues out to nearly 1,000 astronomical units, with some Kuiper Belt objects on orbits that reach even farther beyond that. So while the asteroid belt and Kuiper Belt share some similarities, as you can see, one is vastly more expansive than the other. And while we may have reached the end of the Kuiper Belt, there's still another massive structure that surrounds every other object and belt I've mentioned so far. In a recent video, I talked about the Oort Cloud, the colossal structure of orbiting icy debris that encircles our entire solar system. It's so jaw-droppingly far away that even our most powerful telescopes can't catch a glimpse. So how do those two structures, the Oort Cloud and the Kuiper Belt, differ from each other? For one, the Kuiper Belt is thousands of times closer to the Sun than the center of the Oort Cloud, which is theorized to stretch from 2,000 to 100,000 astronomical units. Another major difference is that the Kuiper Belt is donut-shaped, while the Oort Cloud is spherical, like a gigantic bubble of swarming debris. But something these structures do have in common is that they are both sources of the celestial phenomenon that we know as comets. The Oort Cloud is the source of many long-period comets, while the Kuiper Belt is where some short-period comets are born. While the Kuiper Belt today is one of the most massive structures in the solar system, it's just a small fraction of what it once was. Originally, altogether, it probably contained 7 to 10 times the mass of Earth, but the shifting orbits of the 4 giant gas and ice planets caused most of that to be lost to space. What remains is no more than about 10% of Earth's mass. Not only that, but the Kuiper Belt today continues to slowly erode away. As objects occasionally collide and break apart, smaller fragments are left in their wake, and some of the resulting dust is blown out of the solar system by the solar wind. Sometimes these collisions, or Neptune's gravity, will cause Kuiper Belt objects to head on a new path towards the Sun, creating short-period comets which have orbits of less than 200 years. Over time, the Sun's radiation causes comets to shed material, producing the spectacular tails we see from Earth. Several famous comets originate from the Kuiper Belt, or scattered disk, including Halley's Comet, with an average orbital period of 76 Earth years, or Comet Shoemaker-Levy 9, which broke apart and smashed into Jupiter in 1994 in the first ever observed collision of 2 solar system bodies. As we all know, Jupiter survived, but the impact was visible from Earth and was quite a spectacular sight to behold. You can see it out for yourself if you check out my video on the aftermath of this collision. You may also have heard in the news recently about a near-Earth asteroid named 2024 YR4. While there is a very, very small chance of this asteroid colliding with our moon, or even a smaller chance of it impacting Earth, the short-period comets originating from the Kuiper Belt pose no immediate threat to us in the next 100 or more years. In other words, you don't need to worry about that. Despite the Kuiper Belt being just a small remnant of what it once was, it still offers a nearly endless frontier of objects for us to explore. And unlike the Oort Cloud, which we have not been able to visit yet, we have been to the Kuiper Belt. While most of what we know about the Kuiper Belt comes from ground-based telescopes and the Hubble Space Telescope, NASA's New Horizons is the only spacecraft to have actually been there. It performed a flyby of the dwarf planet Pluto and Kuiper Belt object 2014 MU69, which was later officially named Arakoth, meaning sky, in the Native American Powhatan or Algonquian language. This flyby of Arakoth in 2019 was the most distant flyby in the history of space exploration, taking place 1.5 billion kilometers beyond Pluto, with the New Horizons spacecraft getting as close as about 3,500 kilometers above the surface of the object. And even among the swarm of mysterious objects that make up the Kuiper Belt, Arakoth still managed to surprise the New Horizons team. Its strange shape was unlike anything we had ever seen in our solar system. Arakoth is a small icy KBO known as a contact binary, composed of two distinct lobes that at some point merged into one body. Its shape resembles a flattened snowman. At just 35 kilometers long, 20 kilometers wide, and 10 kilometers thick, you might not think there's much to learn from this relatively tiny object. But what Arakoth lacked in atmosphere and diverse geology, it made up for in its unique structure. The bizarre pancake snowman shape of this Kuiper Belt object provides crucial insights into how planetary building blocks came together in the early solar system, and how planets may have formed. Arakoth's shape seemed to give it a counterintuitive gravity field and rotation, and several papers published since the flyby have led to an almost undeniable truth about how planetesimals form, something the New Horizons team didn't expect. Planetesimals form when smaller objects come together to make larger bodies, which may eventually combine to create a planet. Until now, there have been two competing theories: hierarchical accretion, which proposed that small objects would crash into each other at high speeds until they created something bigger, and local cloud collapse, where nearby objects would slowly come together because of their gravitational attraction, thereby forming larger and larger bodies. And now, thanks to the Arakoth flyby and important research into the object's geology, geophysics, composition and formation, we can be fairly certain that the theory of local cloud collapse is correct. The object's smooth surface and the lack of fractures from stress confirm that the cosmic snowman formed at low speed. Alan Stern, a planetary scientist and the lead for the New Horizons mission, said that the evidence was so strong, we've decisively solved a multi-decade debate about how planetesimals form. And thanks to New Horizons, we get to see the most famous Kuiper Belt object, Pluto. The spacecraft performed a flyby in 2015, allowing us to get up close and personal like never before and take those stunning images. The mission collected observations of Pluto and Charon, the dwarf planet's largest moon, and was able to collect data on Pluto's other satellites, Nix, Hydra, Kerberos, and Styx. Of course, we've all seen the stunning photographs of Pluto's heart-shaped surface region, also known as Tomba Regio. But did you know that the heart-shaped feature is actually a glacier? The western lobe of the heart, named Sputnik Planitia, after Earth's first artificial satellite, Sputnik 1, is a vast nitrogen glacier that stretches 1,000 kilometers wide and 4 kilometers deep, and is undoubtedly the largest known glacier in the solar system. The eastern lobe of the heart gets its light color from nitrogen that is carried from Sputnik Planitia and deposited as ice. Not only did we get stunning images of Pluto, but the data from New Horizons forever changed how we understand our favorite dwarf planet. It revealed that Pluto is far more complex than we previously thought, and offered clues to the origin of its heart-shaped feature. The data led some to believe that Pluto's heart-shaped region could be explained by an internal water-ice ocean. However, a recent study led by astrophysicist Harry Ballantyne from the University of Bern has revealed another, more likely culprit. The heart shape may have been caused by a low-velocity impact that left a gigantic splatter across the surface of Pluto, creating the western half of the heart shape. This impact would have come in at an oblique angle, as in not straight on. Imagine throwing a water balloon across dry pavement in the same way you might skip a stone across a pond. When the balloon scrapes the pavement, it pops, leaving an elongated splat of water across the pavement. This kind of angled, low-velocity impact is similar to how the western lobe of Pluto's heart feature may have been created. But it's not just Pluto that we get to see up close. The images of Pluto's moon Charon were also incredible. Can you make out the enormous equatorial tectonic belt? Its existence suggests a long-gone water-ice ocean on Charon. So what comes next in our quest to understand the Kuiper Belt and, consequently, to understand our solar system? New Horizons is expected to exit the Kuiper Belt sometime between 2028 and 2029. And while there is no current target for a further flyby, it is possible that NASA identifies another suitable target. New tools like the James Webb Space Telescope could help us to further analyze the composition of Kuiper Belt objects. And perhaps in the distant future, a robotic mission might allow us to land on one of these mysterious objects, or even collect a sample for a return mission back to Earth. Who knows what else we'll discover out there in this vast, frozen frontier. As technology advances, future missions will hopefully push deeper into the Kuiper Belt, revealing more of its long-held secrets, one icy world at a time.